Yes?
But the points on the extreme ends, they have a huge distance.
Yeah, this is topological.
No, I'm asking you clearly. I mean,
No,
with respect to the metric.
okay, with respect to the metric, the hyperbolic metric, you mean? Yes, the surfaces has very different shapes.
Okay.
The surface may have very different shapes. Yes.
Is there a classification for these things as well?
Yes. So I explain what is the classification? What is the
Teichmüller space.
huh?
The Teichmüller space.
Yes, exactly. The Teichmüller space is the space of all different shapes. When two shapes are the same, when they are isometric, then they are in the same point in the Teichmüller space.
So the 6G minus 6,
Yes.
it covers this as well.
It covers this, yes. It is a space of parameters.
Okay.
It is this space of parameters. Yes.
Yeah, so let's start today's lecture. That's a 2 hour lecture with a small break. And there will be a group photo session at 4 p.m. And please call all your friends who are registered and are not here.
Okay, thank you. So I answer again to this question here. For instance, now we are talking about surfaces not only topological but equipped with some hyperbolic structure which we cannot visualize. But some of the properties we can represent on the picture here. So this is a surface of genus 3 with a long tube here, very long tube. And let me take another surface here. With a long tube here. In fact, they represent different points in Teichmüller space, even if they are isometric. Even if I turn this surface from left to right, and I can put it isometrically on the other one, they represent different points. And this is because of the following notion. In fact, there's a notion of marking of a surface. It could be of a topological surface or geometric, say hyperbolic surface, or even if it's on the torus, I have the marking of the torus. So let me tell you what is the marking. What is the marking of a surface? Because this plays an important role here. So this is a fixed topological. I take a fixed topological surface. It is fixed through all the rest of this course. And now here I have hyperbolic surfaces. And for each hyperbolic surface, I must choose let's call it let's call it H. This is my my hyperbolic surface. G is, no, I don't want G because we use G for the genus. M metric. This is the hyperbolic metric. And here I have the surface S equipped with a hyperbolic metric N. What is a marking? This is a marking. Let me try to write a precise formula. A marking of SM is a homeomorphism defined up to homotopy. And now I need you to know this word. So your professor told you what is a homotopy? So this is a homeomorphism defined up to homotopy in the sense that if I modify H by a homotopy, I get the same marking. I get the same marking of this surface. Yes. This surface, I didn't give it a name. Let's call it. Yes. I want a standard surface called X, which is fixed once and for all, and which will serve only for the marking. I don't want. I will not put any geometric structure on this. This is. So before putting the geometric structures here, I need a marking, and I will tell you why. Okay. Let me give a reason in advance. So if I tell you, well, Teichmüller space is the space of all hyperbolic structures on a surface, on a given surface, if I say it like this, then this space is infinite dimensional. Because a hyperbolic surface is just, you see, I can move this hyperbolic structure by some homotopy on my surface. I will get also another hyperbolic surface. Okay. If you think of a hyperbolic surface as a Riemannian metric, you have a scalar product on each tangent space. Then you can move it from point to point, the scalar product, and you can deform it in infinitely many ways. So there's no way that the resulting space is of dimension 6G minus 6, like we said last time. Okay? And the space will be of dimension 6G minus 6. This is the space of hyperbolic structures on S up to homotopy. That is, if I vary continuously a hyperbolic structure on a surface, I don't change anything. I am at the same point in the Teichmüller space. This is something you must understand. Okay, so I will formulate my definition now more precisely. So the Teichmüller space of this is S, G, N, C. This is a surface. This is a surface of genus G with n boundary components and C punctures. The Teichmüller space of this surface is the space, well, of marked hyperbolic surfaces up to homotopy. So I'm complicating a little bit the definition, but this is much more precise. I gave you the idea before. Now you must deal with the marking. You see, if you consider the space of the space of metrics on the tori, and suppose this torus is the quotient of a square of the plane, and then okay, I will tell you. You see this figure here. I can turn it, and then I get also a tori. I get also a torus, and so they are isometric because I'm doing the Euclidean metric of the first torus is isometric to the Euclidean metric of the second torus. They are obtained just by some rotation. The rotation preserves the metrics, but it's a different surface. It's a different point in Teichmüller space because the marking is different. This rotation here, which I talked to you about, is not a homotopy. It's not homotopic to the identity. It's yes. Okay, so let me maybe you will understand more when I will say a few things about this. One important thing is that on a marked surface, I can talk about the homotopy class of some closed curve. Okay, from now on, when I say a closed curve, I mean a closed curve which is not contractible to a point. If I talk about this closed curve, I'm not interested in this closed curve which I can homotop to a point. Okay, this is a closed curve. In fact, the term is essential closed curve, but I will delete the term essential. I'm always talking about essential closed curve. This closed curve, I can shrink it to a point without harming the torus. The torus will stay a torus. If I shrink this curve here to a point, then the topology of the torus will be destroyed. Then I will have here it will no more be a surface. Okay. So okay, on a marked surface, I can talk about the homotopy class of any closed curve. Any closed curve has. Now we know that what is a closed curve? It must not be shrinkable to a point. And okay, let us draw some closed curves. Some closed curves on this surface. This is a closed curve, right? It's not shrinkable to a point. You understand this? This is a closed curve. It's not shrinkable to a point. This is a closed curve. This is a closed curve. This is a closed curve. And then I have one here. I have one here. And then I have more. Do I have more? I have many more, right? So you're right. So say I can start with this, and then go and then here. So this is now a new closed curve, which I obtained from the first one by going like this, okay, etc. The set of closed curves on the surface is a rather complicated set, and I want to show you a first picture. I want to show you a first picture. Okay. So I need the other. I need this thing. Thank you.
Are these curves called essential curves, or is there more?
Yes. Yes. Essential means non-homotopic to a point. Yes, not to the boundary. I mean, this is a little bit. Some people consider them also as essential. Some people. Okay. Now let's talk about surfaces. So this is a picture I wanted to show you, and it's drawn by Thurston. In fact, I have these notes from the first lectures he gave on this. He drew here a typical simple closed curve, so more complicated than the one I drew here. And okay. I said that when I say a closed curve, then I want it to be non-homotopic to a point. Then I said this curve here is homotopic to a point, so I don't want it. There's a theorem, in fact. It's a theorem in topology of surfaces. It's one of the first theorem I learned. One of the first theorem I learned. It says that a closed curve a closed curve in the sense we said that is injective. So let me put here. Simple means injective. That is, I'm not considering curve with double points. Just injective. Injective maps from the circle to the surface. Okay, injective maps from the circle to the surface. So, simple injective closed curve on the surface S. He doesn't call it. So is non-homotopic. Non-homotopic to a point. Is non-homotopic to a point if and only if it is not the boundary of a disk on the surface. So, so here, for instance, I told you that this curve I'm not interested in because it's the boundary of a disk. Right? This theorem is not, I mean, it's a difficult theorem. I told you this is the first theorem I learned when I started studying surfaces. This is one of the 2 or 3 results which are in a paper by David Epstein called Curves on Surfaces and Isotopies. I think this is the title of the paper or something like that. And it's a paper which appeared in Acta Mathematica. It's a journal. And in the 1960s, I think, this is it is a long paper. So you see, when I told you that I want to disregard these curves because they bound a disk, and then I show you a typical closed curve like this. How do you know that this curve here does not bound a disk? Maybe it bounds a disk. I don't know. I never tried to figure out. Right? So it's in fact it's a question. In fact, it's a problem. I'm not sure if it's completely solved, or you see, such problems may have different kinds of solutions. The problem is to find an algorithm which says when I draw a curve to know whether it bounds a disk or not. So this is a complicated way of drawing a curve. I mean, there will be no algorithm which will solve the problem for this curve like this. But we discussed last time, or the time before, in fact, the fact that a surface of genus 2, a closed surface of genus 2, you can realize it and then C, D, C inverse, D inverse by gluing the 8 sides of an octagon in this way. Okay? We did this for hyperbolic surfaces, but now it's not hyperbolic. It's just, we are talking just about topological things. So I take this Euclidean octagon, and I do my gluing. I know that I will find a topological surface without boundary of genus 2. Okay? Now, when I have this method of constructing the surface, Well, I can draw curves on this diagram here. For instance, I can start here and go there. It will give me an arc on the resulting surface. Okay, but this point will be identified with this point on the quotient, so I can continue. My goal is so I continue here and A. So then I will start here again. Wait a minute, let me continue. So I started here. I started here, and okay. I can go here, and then the C, where is the C? This goes here, and then I'm stuck here. I will go to the D, and then the D is here, and I must necessarily go to the A, and the A. Okay, no. Let's go here. Let's go here, and then I come here, and then I continue. In fact, I want to continue. I want to continue until I reach a point which is this one. In fact, I could have stopped here. No, I have to do more. I have to do more so that my curve is closed, so that at the end I arrive to the same point, right? So this is a method of drawing curves on surfaces. And then I tell you, well, okay, now can you, when I do such a thing, I mean, you give a method of joining. You want to join the points which are identified. So how do I recognize in my way of drawing like this that the curve is homotopic or not to a point? This is not an easy problem. And it uses the fact, I mean, some way or another, you must use the fact which I erased, which tell you that, well, your curve is homotopic to a point if and only if it is the boundary of a disk on the surface. And here I cannot see yet whether the resulting curve is the boundary of a disk on my surface. Okay? This is a typical problem of topology. If you think about this problem and you try to figure out one solution to this problem and so on, then you learn a lot, and then you become a topologist. Okay, so this is one of the things I wanted to tell you, and then let me.
You all MSc students learn quotient spaces, right? So these identified sides.
Yes, well, this is a very good question. So when you try to classify and so on, you want to find invariance, numerical invariance, or algebraic invariance, or so on. So you say, okay. In fact, these A inverse, B inverse, when you identify them. Thank you. When you identify, no, I don't want this anymore. Yes, I just need the light. Yes. So something which I didn't tell you. In fact, I said, but so when they are on the resulting surface, you have A, B, and then C, and D. The A, B, C, D on the resulting surface are generators of the fundamental group of the surface. So our colleague, when he says, when he asks whether there's algebraic invariance or so on, I mean, one of the questions is you have you have a curve on the surface which is written in terms of the generators of the fundamental group, and this is now algebraic, and you want to know whether it is zero, it is the identity map in the fundamental group or not. So yes, this is related to this problem. I mean, there's a lot to say about this in algebraic topology. No? You define an element of the fundamental group as a word in the generators. So is there an algorithm to say whether this word is the identity element of the group or not? And there's a huge research on this, people doing group theory from this point of view, the geometric point of view. Then the results say, well, fundamental groups of surfaces have a solvable word problem. That is, there are algorithms to know if an element of the fundamental group of a surface is the identity element or not. This is a solvable problem. But there are groups with non-solvable problems, and there are complications and so on. So this is, these are central problems. You know, when we start thinking about curves on surfaces, we hit complicated research problems. Okay, so so why am I talking about this? Let me remind you that we talk about a marking of a surface. In fact, to define the marking, I tried to do it precisely. It's always more complicated than what is the real matter. You see, I have a surface. Again, I have this surface, and I have this curve, and I have this curve. What is the difference between this curve and this curve? Is there any difference between this curve and this curve? I'm not talking about the length of the curves, just these two curves as closed curves. Huh?
Are they homotopic? That's what you asked?
Yes. So your professor says these curves are not homotopic. So, but when I defined the surface, I didn't. So talking about a marking from a given fixed surface to this one here will allow me to say that well, this curve is different from this curve because they correspond to different homotopy classes in a fixed surface. So these curves are not. So you see, these curves are not homotopic, but I may have. You see a hyperbolic structure. I may have a hyperbolic structure which is very symmetric with respect to this plane here or to this curve here. That is, there's an isometry. There could be an isometry. Which takes me this part of the surface to this part of the surface, but still, even if geometrically the two surfaces are the same geometrically, if they are isometric, I want to say that this curve is different from this one. Why do I want to say this? Because there's something called the length spectrum of a surface. So among the people who know, can you tell me what is the length spectrum of a surface?
It is the length of the path of the code graph.
Yes.
So
the length spectrum, there's the word length here. So this is the set of lengths, well, of the simple closed, yes, geodesics. Here, let's say I have a hyperbolic surface. And one thing which is true, if you say it precisely, is that the length spectrum of a surface determines the isometry class of the surface. It determines the geometric structure. So a hyperbolic surface, I can characterize it by the length of its simple closed geodesics. But here, in fact, the length structure of I want to put marked hyperbolic surface length of because for me this, you see, this even if there's some isometry which may take this side to this side, but I want to consider them as different surfaces, and this is why I introduced the marking. So here I want to say that this is the interesting part, the marked length spectrum. When I have a surface like this, I want to tell you, well, the length of this closed geodesic is 2. The length of this closed geodesic here, when I have a hyperbolic, when I have a metric, I can measure lengths. I can measure lengths of curves. Okay, hyperbolic metric. Well, a metric on some space allows me to measure distances between points, but it allows me also to measure lengths of curves in the usual way, in the way Archimedes did, in the way by taking points here, measuring the distance between this and this, measuring, and then taking more closer and closer points. And this is, I mean, this is what you learned in whatever, in measure theory or in even in Riemannian geometry. You see, well, how do you measure the length? When you have a metric space, you measure the length of a curve by taking points and then approximating your curve by taking closer and closer points, and if it converges, then you say that the length is finite. Anyway, so the important thing is that the important thing we have to remember. The important thing we have to remember is that again, a marked hyperbolic surface, I'm going to write the same thing because it's important, is determined by its marked length spectrum. So let's now write again this definition. The Teichmüller space of topological surface of genus G, say with n punctures and C boundary components, but let's stick to this case without complicating with functions and so on. Teichmüller space. Now this is the space. Now I want to put homotopy classes, because I told you that if two hyperbolic metrics, or if two metrics are homotopic, I consider them as the same. Otherwise, my space is infinite dimensional. Homotopy classes of hyperbolic metrics on I have to put the marking somewhere, of marked hyperbolic metrics on SG. And this is the most precise definition. Now, I didn't cheat you. You have, we didn't forget any word here. Because again, if I don't put the marking, I will tell you, okay, it's homotopy classes of hyperbolic structures, but how will you distinguish this metric from an isometric metric or from okay. So this is the definition now, and then the standard notation here is T with a calligraphic T of SG, or TG, or T if the G is understood. Now we have a space. You have an idea of this space. So on TG, I have functions, and this is very important. When you have a space, you want to study functions. So you know now some functions defined on this space. What are these functions?
The homeomorphisms.
No. The homeomorphisms are okay. I mean, usually when I say a function, it's a function which goes from this space to some numerical space. Yes, tell me. Yes, the length functions. These are the length functions. The length functions the length function associated to simple closed curves. So what are these length functions? Can you tell me more precisely what is this length function? The length of what? Yes. Yes, right. And here we need a result which you must know. So in fact, in each homotopy class of simple closed curve, there's a unique geodesic. There's a unique shortest curve. And when I say the length function associated to simple closed curve, it is the length of the unique geodesic in this homotopy class. Let's write it here. This is not difficult. In fact, this is a proposition. In any homotopy class, of simple closed curves, there's a unique geodesic. Remember, we said simple closed curve means that it's not shrinkable to a point. So, for instance, this one here, I have a unique geodesic. This one here, I have a unique geodesic in this class. So, how do you prove this? This needs a proof, and the proof is not very difficult. In fact, it's a general theorem for negatively curved, not only hyperbolic, but for all negatively curved manifolds. It's an old theorem. In fact, it goes back to Hadamard. He has a paper where he proves this even for variable negative curvature.
Unique theorem.
Yes, a unique geodesic. So the existence is not. I mean, the proof is standard. You take the shortest curve, and you show that this shortest curve is a geodesic, in the sense of hyperbolic geometry. In fact, this is not difficult. But you want to say that the shortest curve exists, that there exists a shortest one, and this is general topology. I think by applying Ascoli theorem or things like that, you have curves are of bounded lengths, and then the uniqueness is not completely obvious, but you have to prove it. So the uniqueness yes. Yes. No, because the long tube, it has always this form. Yes. Well, funnel means that goes to infinity. No, but here it's. If you have a long tube, then there is only one. This is, you see, let me tell you why. In fact, you talked about universal cover, right?
Yes.
Okay, so all these surfaces we are talking about, they have the same universal cover, which is the hyperbolic plane, or this disk model. I want to talk about this disk model. You see, this behavior like this of geodesic coming close in the hyperbolic model, the geodesics, when they come very close, then they necessarily diverge, and you have only one shortest distance between them. You can prove this if you know a little bit of hyperbolic geometry. In fact, what I told you is sufficient to prove that you have this situation. And likewise, when I said that there's a unique geodesic, why is there a unique geodesic? Well, let me draw. Let me draw here a random surface. And suppose that in some homotopy class, I have two geodesics, two closed geodesics. So this is one, I represent them symbolically, and then this is second one. You see? So this is a geodesic, and this is a geodesic, and I have a homotopy between them. I have a homotopy. There's a family of curves which takes me continuously from one to the other. This is a geodesic. This is a geodesic in the surface. It necessarily is the quotient of some geodesic in the hyperbolic disk, right? Right? And this is also the quotient of some geodesic in the hyperbolic disk. And okay, so I made them intersecting here. Okay. And you see, this homotopy between this one and this one, it necessarily gives me a homotopy between the homotopy. You see, these curves, the homotopy will take this curve to this curve, bounded homotopy, right? And this bounded homotopy, when I look, so everything that happens in the universal cover is a covering of something which happens on the surface. Then it would give me a bounded homotopy between two curves there, which is not possible because they intersect in this point, and their points at infinity are infinitely far from each other, and there's no bounded homotopy here. This bounded homotopy on the surface would give me a bounded homotopy between two geodesics there, which is not possible. And the same if the curves were disjoint. In fact, it's the same thing. If I had two curves, like you said there, and why couldn't be two geodesics, which would be yes, the same argument, because these two geodesics, which bound an annulus here on the surface, would bound an annulus in the universal cover, because the annulus, you know, I'm not talking about an annulus like this, because here the distance is infinite, is going to infinity from here to here. So I would have two geodesics in the universal cover which converge to the same point, which is impossible. In fact, we know that in the hyperbolic plane, if I take 2 points on the boundary, there's a unique geodesic between them. Okay, so this is important. And now I state this. Yes.
Do these unique geodesics
Yes.
converge to the boundary of pairs of bands?
Now, if the pairs of pants, no. There are geodesics which converge to boundary of pairs of pants, but not this one. This is just a unique closed geodesic in some homotopy class. So your friend here is asking, you know, I had this picture at the beginning of my lectures, and with geodesics converging to boundary of pairs of pants. No, this is not. This behavior would be just in the universal cover. You have. So this curve here would have a lift here. This curve here, which converges in this to this boundary of the pair of pants, would be like this, like this, and then from the other side it converged to the lift of this geodesic, which would be this one. So, okay, but it cannot converge to. So, in other words, it cannot converge from both sides to the same boundary of the pair of pants. It's spiraling along different boundaries.
So all hyperbolic surfaces have the same universal curve.
Yes, all of them.
Doesn't matter how genus punctures.
Doesn't matter how genus or punctures. Yes. Surfaces with boundary, this is a little bit different because you have boundary points. You have boundary points, and the universal cover also must have some boundary. So the universal cover of this is part of this hyperbolic disk.
Hyperbolic disk or hyperbolic plane.
Or hyperbolic plane, yes. Yes. So let me say this important statement. Let me say this important statement that on this Teichmüller space, Tg or T, I have length functions associated to simple closed curve, lengths of closed geodesics in each homotopy class. Okay. I said that length functions and the length functions, how many length functions I have? I have infinitely many, right? Because the homotopy classes of the simple closed curves, I have infinitely many homotopy classes. You see, as I said, I have my surface. This is a homotopy class of a simple closed curve. Then what I can do here. This is another homotopy class, and then I can twist again and again and again. I get infinitely many. I cannot do the pictures, but okay. No, not free. There is one relation. It's one related group. If for surfaces with boundary, it is free group, but for closed surfaces, there is one relation. So you see, we had this picture of the right. So if the surface is like the one before, obtained by gluing the sides of an octagon, then we had A, B, C, D, and so on. So this A, B, A inverse, B inverse, C, D, C inverse, D inverse. If you do this product, then it bounds a disk. It's homotopic to a point. So for a general surface, it is a group with A, B, C, D, E, F, and then with one generator, A, B, A inverse, B inverse, C, D, C inverse, C, D, etc., etc. So 4 by 4. The resulting is null homotopic. So these are special kinds of groups called groups with one with one relation, one relator group, and they have a special study. I mean, there are hundreds of people who study just these. Hundreds of people now which study these groups with 2 n generators and one relation. So I was saying here that I have length functions. The length functions associated with simple closed curve, and I insisted on the marking. The marking is the thing which distinguishes the simple closed curve with from one to the other, one from the other. Okay, and then I said that I have infinitely many simple closed curves, right? You remember this? I said that I have infinitely many. I tried to draw a few. You see the infinitely many homotopy classes of simple closed curves. The length function associated with homotopy classes, I forgot to say this. Classes of simple closed curves. Let me remind you of something. Before I continue there, let me remind you of something. I showed you a construction of hyperbolic surfaces. I told you that you can do this by gluing pairs of paths. You remember this? And I showed this is one right-angled hexagon. And then there's another right-angled hexagon from the other side. And then you see, I can take two of these. Two of these pairs of paths. What do I need so that I can glue this side to this side? Yeah, I need them to have the same length. If they have the same length, I can glue without problem. If I don't have the same length, so I have these parameters, and suppose so I glue this one with this one with this one, and this one with this one. I get a closed surface of genus 2. And now, in this closed surface of genus 2, I use these hexagons and so on. So you must be almost sure, in fact, that I must have at least, in these length function of associated with simple closed curve, I have this 1, 2, 3. And then here the same. I have 3 length functions which present themselves immediately to me and which are important. So these 3 length functions. Okay, you have 3 length functions. What other length functions do you have on this? What other closed curves you see on this surface? Well, this one here, since it is perpendicular, it goes with this one here, and then it closes. So in fact, I don't have 3. I have 6. Okay. And now I ask the question: do these 6 length functions of closed curves, simple closed curves, do they completely determine the hyperbolic surface? Do they completely determine the hyperbolic surface? Yes, so your friend here says no. It's not. The answer is not obvious. No. In fact, if I take a surface here now, I take a surface here of genus 2, and I tell you, I know the length of this curve. I know the length of this curve, and I know the length of this curve. Here I have 3, and then 3 more, the length of this closed curve, the length of this closed curve, and then again the length of this closed curve. Does it determine completely my hyperbolic structure? This is a very good question, in fact, and it was an interesting question. In fact, it was an open question for several. I mean, it lasted a few years, not too much, because it's not very difficult. Not very difficult. You remember I told you that the Teichmüller space of a closed surface of genus G. What is the dimension of this space? You remember? What is the dimension of this space? Yes, 6G minus 6. And the good question is whether I can find 6G minus 6 closed curves, homotopy classes of closed curves on the surface, such that if I know the length of these 6G minus 6 closed curves, then the surface is completely determined as a marked surface. And there was some work on this. Some people showed that you need more than 6G minus 6. You need 6G minus 6 plus something. And then it was less and less. And finally, the result, I mean, the theorem is that you need 6G minus 6 plus 1 curve. You need one more curve than the dimension, so that, yeah, this is a result. It's uniquely determined. Uniquely determined, yes, uniquely determined. Uniquely determined. So this is to show you the importance. So I have a big space, Teichmüller space, and I want to find parameters for this space. Yes, in 1 minute I will. Okay, no, maybe after the break, because it's a little bit long. Okay, after the break, I will explain to you more about it. Yes?
Mariam Mirza Khan include something about simple closed curves, counting of simple closed curves.
Yes, so she's asking me about the proof of, I mean, you see, when I draw my surface, then I always draw the same kind of same simple closed curves, or a little bit more complicated this one, or a little bit more complicated, and then I try to draw a little bit more complicated, and I drew one, but I was failing. So this is Thurston here. Okay, how do I do this?
The one you drew earlier, right?
Yes, the one I drew earlier. The one I drew earlier. Yes, it is coming. Okay, so this is a simple closed curve. And let's suppose that it's, this picture only suggests a homotopy class of simple closed curves, right? But in this homotopy class of simple closed curve, if the curve is not homotopic to 0, then it has a length. The smallest curve in this homotopy class, the unique geodesic in this homotopy class, it has a length, right? So every simple closed curve, whatever complicated you draw it, will have a unique geodesic representative. And your professor asked me about this problem of related to the work of Mirzakhani, of course. So what is the growth rate of the length of simple closed curves? So if I tell you, if I have a surface of genus 2, how many simple closed curves I have whose length is less than 1,000 or 2,000? Or, of course, it's not in terms of numbers, but you ask whether the growth is exponential or something else, or yes. So this is the problem of the growth rate of the length of simple closed curves. It's important because, as we said, giving the length of the simple closed curve determines the surface completely. So now the next question is about the growth rates of the other curves. So here, for instance, when you glue these two pairs of pants to have a closed surface of genus 2. Okay, now I want to draw the other simple closed curves on this surface. So you see in hyperbolic geometry, in the hyperbolic plane, when you have a line, then you have another line. Another line, either it coincides or it cuts it transversely. It cannot be tangent, and it cuts it here one time. So here I have another curve which when it starts here, it must go here, it must go here, it must come here, and then it must come here. And then you want an algorithm. You want an algorithm that draws for you simple closed curves. That is, you don't want the curve to intersect itself. So at some you don't want this to happen. You want curves with which are non-intersecting. You want an algorithm which gives you curves which are non-intersecting. And then when you find that this problem is too hard for you, or when you find that, okay, everything is known, in fact, on this problem, then you ask about closed curves which have one intersection point, only one intersection point. And this, I can tell you that not many people know a lot about this. I'm looking at closed curves, not simple, not injective, but with one intersection point. So, for instance, this one here, and then one point, only one point, and then injective. Yes, yeah, you can leave it because I. Okay, so we a little bit of. So if you have questions, you can ask me after the break.
So, yeah.
Okay, so I have this. We have this space here, this Teichmüller space. We know parameterization of this space by length functions. I have some functions on this space. When I know the function, when I know all these functions at some point, then it determines completely the point. There's another parameterization. This is called Fenchel-Nielsen parameterization. And this now I'm answering a question which was asked by someone on the web. So what is this Fenchel-Nielsen parametrization? Again, I take some Pants decomposition of the surface, decomposition into pairs of Pants. So these are now geodesics. I take a geodesic pair of Pants decomposition. Pants decomposition, meaning that all these curves are, sorry, I forgot one, all these curves are closed geodesics. And since they are, you see, I start with a topological pair of Pants decomposition that is just homotopy classes of disjoint curves, and then I make them all geodesic, and I explained to you that, did I say, or I say it now, that if, so on the surface, if I take this curve, and if they are represented by disjoint curves as topological curves, then the geodesics in their homotopy class are disjoint. I told you that in each homotopy class of curve, there is a geodesic. If the curves are disjoint, then the corresponding closed geodesics are disjoint also. This is some easy hyperbolic geometry, as I told you, in fact. Yeah, okay, I take disjoint simple closed curves, maximal number. I take the corresponding geodesics, and I find this geodesic decomposition into pairs of Pants. I have the length function, L1, L2, L3, L4. So we already discussed this problem. If I give you the values of L1, L2, L3, L4, L5, so all these functions, if I give you all the lengths, do I determine the surface? Is the surface completely determined? No, because instead of gluing like this, I could change the twist, right? I could change the twist. So there are associated to a geodesic pair of Pants decomposition. So there's associated length parameters, and then twist parameters. Length parameters and twist parameters. The twist is some. It needs some convention, but you can imagine that I can. So here between these two surfaces, I just have. I have a tube here and a tube here, and I want to. They have the same length, of course. They have the same length, and I can glue them, and I get a genuine hyperbolic structure. You see, around each point, there's a disk which makes it, which makes this neighborhood of this point, neighborhood of a point in the hyperbolic plane. Okay. So everybody believes now that there are lengths and twist parameters. Okay, and this is what makes the space, this space of dimension 6D minus 6, because if you make the count, then you find this number 6G minus 6. This is the Fenchel-Nielsen parametrization. You must, yeah. So I wanted to point out something. You see, if I do a full twist, what happens if I do a full twist? So no, not 180 degrees. I think I can count now better than you. It's 360 degrees. Okay. So if I cut the surface, then I turn by 360 degrees, and I glue again. Do I get the same surface or not? No. So our friend here knows that the answer is no. So for the others, you must remember that the surfaces are equipped with a marking. And when I say that the surfaces are the same, it means that the marking, you see, imagine a segment here, let's say a geodesic segment of this closed curve. The homotopy class of this initial closed curve, which where is my initially suppose I have a closed curve like this. After I do the full twist, the new homotopy class is this one in white. So the marking has changed. So these are different points in Teichmüller space. Okay, this is. So this is one parametrization of Teichmüller space. There are other parameterizations. This is the most ancient one and the most, I mean, the one which is natural, which everybody can understand. Last time we talked about. I started talking about measured foliations. And then I told you that there's a space here, there's a boundary. There's a boundary to Teichmüller space, which is a space of measured foliations. And I want to explain this a little bit because I will have to use it later. So if you remember, we discussed foliations on surfaces, and we said that if the surface is not the torus, like here at surface of genus 2, that we must have necessarily singular points for a foliation. Okay? So one can imagine all kinds of singular points, but in this theory, there are only are allowed the following: allowed singular points. So either this one like this, or this one like this, or this one like this. So this is 3 prongs, or 3 separatrices, let's say 3 separatrices. 1, 2, 3, they separate into 3 portions of the plane. 3 locally, you have 3 separatrices, you have 4 separatrices, 5 separatrices, and so on. And this is one. Well, now I want to show you this. How do we do? We do this, and then we close the light. Where?
That's the remote.
Okay. It will come. Okay, so this is again, I like this picture. This is the first time Thurston talked about this. He distributed these notes. So this is interior singularities of measured foliations, p-pronged saddles. So this is p equals 3. This is p equals 4. And this is p equals 5, as I said. And then he has this picture. I mean, I have this picture, which is the last picture. Now, something important is when you have two measured foliations which are transverse to each other. So these foliations, and then you have one which is transverse to it, but here he is explaining what happens at the singular points. So they are transverse, and then at the singular points, the most natural thing happens. This is a 5-pronged singularity. No, sorry, it's a 3-pronged singularity for each of these measured foliations, and then they come. So the one is transverse to the other means that at the singular point here, you have the 3 alternating prongs. And in the most natural way, this is 1, 2, 3, 4 and 4 is 8. And these are the only two singular points on this picture. And we talked about geographic maps. You know, geographic maps. You have also these perpendicular foliations by the parallels and the meridians and so on, and you are looking for best maps. And here also you will look for best maps between surfaces. All this is related, in fact. Okay, so I finished now with this picture. And I will tell you more about measured foliations now. Yes. Okay, thank you. So what do you do with measured foliations? In fact, I have a surface, and now I have a measured foliation on the surface. As I told you, it's a foliation. Also, with the fact that it is measured means that when I take a transverse curve, I get a number. I can measure the length. It's not the length. I can measure the measure of this transverse curve. Okay. So now I take this. I call it S. This set of simple closed curves. And we said, we agreed at the beginning that when I say simple closed curves, it means that they are not homotopic to a point. I'm not interested in closed curves which I can shrink to a point. And then I have a measured foliation. F is my measured foliation. And if I take gamma, an element here, there's something called I f of gamma, which is the intersection number of gamma with f. And what does this mean? I means intersection, and what does this mean? it means that this is the minimum or the infimum, but it will be a minimum, the minimum of the transverse measure over all curves in the homotopy class gamma. If, okay, let's come back to hyperbolic geometry. If the surface is equipped with a hyperbolic structure, and I take a simple closed curve gamma, then I can get a number which is its length, the length of gamma with respect to this hyperbolic structure. Okay? Now, instead of a hyperbolic structure, I have a measured foliation. Gamma, say, is gamma is this curve like this. This is I can measure this. I can measure this transverse measure of gamma because I have this foliation. You see, I have this foliation, and I take the smallest one, in fact. Because gamma is a homotopy class, it's represented by curves which are not homotopic to a point. I take the infimum. Now you may tell me, okay, why is the infimum non-zero? In fact, it's like for simple closed curves on a hyperbolic surface. Why is the infimum of a homotopy class non-zero? Infimum of the length of a homotopy class non-zero because it's like this, because life is such that of course there's a proof which is not difficult at all, but the thing which I'm saying is that on S, on this space S, I have length functions. This we did in detail. And length functions associated with hyperbolic structures. And we have transverse measures associated with measured foliations.
So what
yes.
Simple closed curve is part of the leaf of that, right?
No. Yeah, you are right. It can be part of the leaf. It can be part of the leaf of the measured foliation. Then its transverse measure is zero. You are completely right. What I'm saying here is that okay. Let me write it. Let me write it here. It's something which is analogous to what I said for hyperbolic structures. You remember I said that length spectrum determines the hyperbolic structure. Right? Now what I want to say is that transverse measure determines the measured foliation. That is, the spectrum of transverse measures on all these elements of S determines the measured foliations. And then you have the same questions as for hyperbolic structures, given measured foliations. To determine completely the measured foliation, how many transverse measures of curves do I need? The same question as we asked for the hyperbolic structures. And I mentioned, after a question, I mentioned the growth rate of the length spectrum of hyperbolic structures. There's an analogous theory for growth rate of transverse measures on the set of simple closed curves. Yes. Okay, so let me state this theorem about the compactification of Teichmüller space. So something which I will not talk too much about, but you see, as we said last time, I have a pair of pants, and then I can draw measured foliations on this pair of pants. You remember for hyperbolic structures, we said that the three lengths of the three boundary components of the pair of pants determines the pair of pants completely as a hyperbolic surface. Here also the length, well, the transverse measure of the three boundary components of the pair of pants determines the measured foliation. On the pair of pants. So you can glue measured foliations on pair of pants, and you have also Fenchel-Nielsen coordinates. Of course, Fenchel and Nielsen did not know anything about measured foliations, but you also have Fenchel-Nielsen coordinates for measured foliations. So I want to recall, I want to tell you, I'm skipping a little bit of the theory, but I want to tell you that theorem of Thurston on the compactification of Teichmüller space. Okay, so we have again S, simple closed curve on the surface, and I recall that simple closed curve means non-homotopic to a point. I have this space of, well, this is the space of positive functions, space of functions from S to the positive numbers. I'm using Thurston's notation. So I say that, well, Teichmüller space is a subset of this space. Do you understand this? I mean, I tried to explain this today, that any hyperbolic structure, any element of Teichmüller space gives me a function on the homotopy class of simple closed curve. This is the length function. And I explained to you also, I tried to explain that length function determines the point on Teichmüller space, right? So I have here, I put equality is not equality. This is, I have an inclusion, in fact. This map is injective. Okay. It's an injective map. Now I have my space of measured foliation, which I call MF. And I also explained to you that intersection functions, in fact, I didn't say it this way, but the intersection function of a measured foliation on all homotopy classes on simple closed curves completely determines the measured foliation. I gave you just some idea on one pair of pants, and then you have to group pair of pants and so on. There's some work to do here, like for the hyperbolic geometry case. Okay. What I'm saying by this inclusion is that if I have a measured foliation on the surface, and if I know its value on all the simple closed curves, then I know the value of this measured foliation. Do you believe this? It's something close to what I said for hyperbolic length, because of this, if I know the value of the measured foliation on these on the three components of the pair of pants, then there's a unique way to fit the measured foliation in the pair of pants. And then
same as the fundamental.
Where?
In R plus, the image.
Yeah, positive numbers. Yes, the positive numbers. Now, what I say here is that the images are disjoint. This was your question. The images are disjoint, in fact, and this is a theorem. This is part of the theory.
No, what I meant was that when you're taking length,
yes,
you're going to get countable set.
This set is countable, and this is the space of all functions on this. Yes.
The image in R plus for each means if you take for all S.
S is countable, yes. For any element of S, I'm taking. I have one value, yes. Okay, so now there's a little bit more. And we are almost done. So instead of embedding in this space of functions on S, we embed in the projective space. That is, I want to consider that the projective space is the space of points up to a scalar constant. So what happens to hyperbolic structures? We said that if I give you the collection of all lengths of simple closed curves, then I know the hyperbolic structure. You remember this. If I give you all lengths of simple closed curves up to some multiplicative constant, do I determine the simple closed? Do I determine the hyperbolic structure? Yes, the answer is yes, because you see, for instance, you can think about the area of a hyperbolic surface. The area is fixed. So there's no way of doing dilations on a hyperbolic surface. If the lengths are, the length spectrum up to a constant will give you the length spectrum, right? There's only one hyperbolic structure up to homotopy, which gives you, which is the length spectrum of some hyperbolic structure, okay? So in fact, this is an injective map. This is an injective map.
So when you say that S is countable, are you actually taking the homotopy classes of this non-contracted group?
Yes, yes, this is what I said. Yes, homotopy classes. Yes, I'm sorry. Yeah, this is homotopy classes. Homotopy classes. In each homotopy class, there's one simple closed curve. Yes, so I can. Yes, yeah. Yes, there's only one geodesic. There's only one geodesic. Yes. Okay, now here, this map is not injective. This map is not injective, obviously, because, well, from everything I told you about measured foliations, I can multiply the transverse measure by some constant. I get another measured foliation, right? So this is not injective. This is, but there's this projective space. The projective space of measured foliation, that is the measured foliations up to a multiplicative constant. And the theorem now, the compactification theorem of Thurston is that is the following. So the image of Teichmüller space in this space, we called it P R plus to the S is homeomorphic to an open ball of dimension 6G minus 6. The image of PMF in the same space is homeomorphic to a sphere of dimension one dimension less. Is this 6G minus 5 or 6G minus 7? 6G minus 7. Okay. And in the image, I mean in this image, PMF is the closure in the sense of general topology. It is the closure of the image of T. So this is the Thurston compactification of Teichmüller space. I skipped a few points, you know. So for instance, I didn't tell you that the measured foliations, of course, I have some flexibility. I mean, they are when I say that the image of PMF, you see PMF up to some homotopy, up to some isotopy of the measured foliations. Because when I say that a measured foliation is determined by the intersection numbers with homotopy classes of simple closed curves, if I take a homotopic measured foliation, then it will give me the same numbers, the same intersection functions with homotopy classes of simple closed curves. So this is so in the same way as we had a marking here and we said that we are identifying two hyperbolic structures if they are homotopic, right? Here as well, I'm identifying two two measured foliations if they are homotopic. So, okay, this is the, this is, I gave you three references for Thurston. And now there's this fourth one and the last one. This is called, or it's also a book on the internet. It's called Thurston's Theory on Surfaces. It's not written by him. These are notes written by Fatih, Lodenbach, and Poinaro. So it contains. So what I
We'll go down. Happy. We'll come back for the next lecture by so 4:30. And remember, tomorrow we start at 10. We'll be here on time except for those who are getting late exam. Let's go.
But because of, we are all in teaching institutes and we cannot we have other responsibilities. So I could manage to come only for a kind of 1.5 days. But it's a great pleasure coming here because after coming here, I realized that all the faculty members, math faculty members in your department are my friends or have been my friends. So it's good to see all of them. So thank you very much. So now all of you are listening the lectures by Athanas, and today morning also Athanas was talking about marked hyperbolic structure and hyperbolic structure on surfaces, right? Yeah. So how many of you have seen that? All of you, right? So all of you know what is Teichmüller space by this time. Yeah. So what I will do, I will start with a kind of orientable surface of genus G, and you can have on kind of P boundary components. So I consider boundary components as punctures. Okay. So then what is the Euler characteristic of the surface? Have you seen that? No? So that is 2 minus 2g minus p, and you take it less than of negative Euler characteristic. Because unless you take a surface with negative Euler characteristic, you will not have hyperbolic structure there. Okay. So now you look at the universal cover of the surface. Because I think you also had a course on homotopy and universal cover that Professor Riddhi Shah has lectured, right? So what is the universal cover of a orientable surface of genus G? So this is topologically, these are facts, okay? I mean, you can look at the book by Massey, Algebraic Topology. So some of these stuffs are there. Okay. So there is a chapter on classification of surfaces, and the universal cover plays a crucial role there. So this is topologically a disk. Okay. And pi 1 sigma, the fundamental group. So this acts on sigma tilde by deck transformations. Fine? Yeah. So now, okay, so I am using a bad notation. So this is the kind of projection map. Projection. You should not confuse it with the fundamental group. This is projection. Okay, I mean, I can call it some other notation also. Maybe call it P. Okay, if you want. Okay. Then P of, say, so you take P1, P2 in sigma tilde, then P of, again, I mean, bad notation, so I think I change it by something, maybe C1, C2. Okay. So P of C1 equal to P of C2. If and only if, what would be the condition? C1 should be a translate of C2 for some alpha in the fundamental group. It follows from basic covering space theory. So that means if you take a action of the fundamental group of the universal cover, then the orbits, okay, the orbits kind of gives you a map from the orbit space to the surface, right? So you have a map from sigma tilde mod pi 1 sigma to sigma, and you know, right, that this is actually kind of a homeomorphism. So, and every kind of surface arise in this way. Yeah, these are this follows from basic covering space theory. Okay. So now in Athanas's lectures, you have seen this space, hyperbolic plane, right? He has lectured. So which models he has discussed? The upper up space, yeah, the complex upper up space. Okay. So this is, and this is the boundary, yeah. And what is isometry group of hyperbolic space? That is, no, this is PGL2R. Okay. So the orientation preserving isometries is PSL2R. Otherwise, the full group of isometries has two components, one orientation preserving and orientation reversing. Okay. So now you consider, I consider G to be, I mean, let's look at only the orientation preserving component. Okay. Consider G to be PSL2R, okay, not PSL2R, consider G to be SL2R, the matrix group, or SU1, 1, or SO2, 1. What is the relation between these three groups? They are all isometric groups of different models of the hyperbolic plane. So the first one is for the upper up space, the second one is for the ball model, and the third one is the linear model or the conformal model. I mean, it's a kind of Lorentzian model, you know, like you have a bilinear form of signature 2, 1, and you, I mean, yeah, I think if you don't have seen this, then if I have time, I will discuss this model in more detail. But these are all models of the hyperbolic plane. Okay. So now a representation rho from the fundamental group to this group G is just a group homomorphism. Okay. So now you consider Hom pi 1 G. the set of representations of pi 1 to G. So, the group G acts on home pi 1 G by conjugation. Okay. So, we are interested. Okay. So, this I think let's not talk about this now. Let's first let's not talk about this at the moment. Okay. So, this is a set that I had defined. Now, you consider a map F from sigma tilde to H2. This is kind of equivariant. This is rho equivariant if F rho alpha is rho alpha Fp for all p in the universal cover and alpha in pi 1. Okay. Now, so you now have a kind of rho equivariant family of maps, and you kind of you have this set of representations of pi 1 to G, where G acts on itself by conjugation, and you have the conjugation orbits. Now, what is the correspondence between these two? So, there is a close correspondence, and these two objects give you a correspondence between the topology, geometry and algebra of the representations. So, the correspondence goes like this. So, you have a correspondence between Drake transformation, hyperbolic isometries and matrices in SL2R. And then you have a kind of you have a correspondence between equivariant maps and action by by representations of the fundamental group into gamma. Okay. And then so what, how this correspondence is built? So that is, let me just briefly tell you. Okay. So let me change my slides. So now, to give an indication how this correspondence is built, you recall what was a marked hyperbolic structure that Athanas has talked about in the morning. So, a marked hyperbolic structure on sigma. So, how he defined, can anyone remind me? A homeomorphism. So, I call it a pair M on F, okay, where M is a hyperbolic surface and F, well, I am not considering it as a homeomorphism at the moment. You can consider it as a homeomorphism, but you can consider also is that as a homotopy equivalence. Yeah. So, this will essentially give you the same thing. And you have two hyperbolic structures, So, call them F sigma to M and F prime sigma to M prime are equivalent if there exists an isometry M to M prime. So, now when I am talking about isometry, I am giving them a metric coming from the universal cover, which is the hyperbolic plane. So there is an isometry such that this diagram kind of homotopy commutes. So you have f, you have f prime and this. So this is homotopy. So that is phi compose f is homotopic to f prime. Okay. So now what happened that you have every equivalence class of marked hyperbolic structure. Corresponding to that, you have this you have discrete groups, okay, and those discrete groups are conjugate to each other, because as soon as you have a, or if you consider them as a homeomorphism, like somebody pointed out, maybe it will be easier to understand homeomorphism, then from the universal cover, every such hyperbolic structure is coming from a discrete subgroup of PSL2R. Now, two structures are equivalent, that means the discrete subgroups are conjugate to each other. So, to every equivalence class of marked hyperbolic structures, there is a well-defined equivalence class rho in home pi g mod, okay, it's called home pi g mod g. So this is the kind of conjugation orbits. Okay. So corresponding to every hyperbolic structure, there is a conjugation orbit of representations, and a representation rho pi 1 to g is called Fuchsian if it comes from a hyperbolic structure. Okay. So equivalently, a Fuchsian representation satisfies three conditions. So the first condition, rho is injective. That means the representation is faithful. Second condition, image of rho is discrete in G. So this is a Fuchsian group. And the third condition, rho is type preserving. What does it mean? That means rho of alpha if it so type preserving means you have these loops, right? So if the loop is a closed loop, then it corresponds to a hyperbolic element in the isometric group. So rho of alpha has to be hyperbolic. And if it is near a puncture, then it's a kind of cusp. So rho of alpha will be parabolic element. Okay, so that is called type preserving representations. Equivalently, this means yeah, so let us not write type preserving if it is kind of, but they are the equivalent conditions here. So, equivalently G mod not G mod rho gamma, equivalently yeah, G mod yeah, equivalently what? So, equivalently rho of pi 1 is geometrically finite. That is, it has a finite sided so you know what is the fundamental domain? Anyone does not know what is the fundamental domain? Was it discussed in this course? No. So then I think type preserving is better. So type preserving means
It was mentioned once, but.
okay. So but anyway, so that means in other words, rho is type preserving. That means it maps hyperbolic loops onto a hyperbolic elements and cusps to parabolic elements. And rho cannot, yeah, so pi 1 is a fundamental group of a surface, right? So it can have only two kind of loops. Either the loops is homotopic to a closed curve or the loop is a cusp. So if it is a closed curve, the image is hyperbolic element. If it is a cusp, the image is parabolic element. That's what type preserving means. Okay. So these are the three conditions that a Fuchsian representation satisfies. And this is one realization of the Teichmüller space that you were looking at. So this gives one realization of the Teichmüller space as one of the component of Hom pi 1 sigma PSL2R mod PSL2R. That contains the discrete faithful type preserving representations. So this space Hom pi 1 PSL2R mod PSL2R, this is a space and this space is a disconnected space. It has several components. Now one of the component consists of all discrete faithful type preserving representation. That component can be identified with the space of all hyperbolic equivalence classes of hyperbolic structure on the surface, which is the Teichmüller space that we have seen. So yes. It's a topological space, so it has disconnected space, so it has connected components. So one of the component is Teichmüller space, and it consists of all discrete faithful type preserving representation. So this space has many other components also, and yeah, so this is a kind of space that is this whole space has not kind of been completely well understood till date. But Teichmüller space, I mean, there has been a lot of development that you are already, some of the developments you are already seeing, right? Okay. So
Do we have any information about other component, at least one?
yeah. So you know, there is another component that consists of discrete faithful type preserving orientation reversing representation. That means there is if you give a orientation, then another this is orientation preserving representation. There is a orientation reversing representation that looks just like the Teichmüller space. Now there are I think in between there are 3G minus 3 components. Okay, and how each of the component behave, I don't know. Okay, so that how many components are there in this space, that is also a kind of deep problem. And there are works by William Goldman who understood it to some extent. Now, this correspondence between the correspondence between Fuchsian representation and hyperbolic structure, etc. These follow from classical work of Fricke Klein and Andre Weil. So yeah, so I will Klein groups, yeah, Kleinian group, yeah. So there, you take, so more generally, that was my next thing. More general, I am taking a slight digression here. More generally, you take any Lie group. If you don't know Lie group, you don't worry. Take matrix group, any matrix group, yeah, any linear matrix group. Then GLNR, yeah, subgroup of GL and C, closed subgroup of GL and C. Okay. Then home pi 1 G, you can consider it, there is a map from home pi 1 G to G to the power n, where n is number of generators of pi 1, the fundamental group of a surface. Okay. So what you do, you take rho and then you map it to rho gamma 1, rho gamma n. So this way, this space can be considered as a subspace of G to the power n. Now this is a Lie group, so it has a nice smooth structure. So home pi 1 G can be considered as a subspace of G to the power n. And from there you can get the topology, but smoothness needs to be verified, right? You know, right, that subspace of a smooth manifold may not be always smooth, that you know, right? So it may not be smooth, but it has a nice topological structure. And if G is a algebraic group, then this space home pi 1 G is an algebraic subset of G to the power n. So if G is the algebraic group, that means if you can think of G as a zero set of some polynomial, then home pi 1 G is the algebraic subset of G to the power n, and you can also view it as a algebraic object. Okay. So now the point is, this group, automorphism group of the fundamental group times automorphism group of G, that has a natural action on home pi 1 G, and the action is given by rho alpha. So how the action goes, you take phi, you call it phi, okay, phi alpha. You take a element rho from home pi 1 G, then this goes to alpha compose rho compose phi inverse. This is a natural action, yeah. So in particular, if you consider alpha kind of to be identity, okay, then you have a nice quotient, right? So mostly G is any Lie group, or yeah. So mostly the quotient home pi 1 G mod pi 1 G, which is the representation modulo identity times inner automorphism of G. So this is same as representations up to conjugacy. So when you take inner automorphism, it's just the conjugation action. So it means you take the conjugation action of G on this representation space and you consider the conjugation orbits of all these representation. So that's this space. Okay. So this space is of much interest, and depending on the Lie group G, the understanding of this space changes. So in the previous few minutes, I discussed only this case when G equal to PSL2R, which is the Teichmüller space. But if you change your Lie group, your understanding of the so this space sometimes is known as a deformation space of a representation. So this deformation space changes, and the geometry, topology and algebra of this space can be very different from the low dimensional case. Okay. So nowadays I think there is a kind of it's a kind of trend, modern trend to look at the spaces when G equal to SLNR or when G equal to SLNC. So there are analog of Teichmüller space in these setups. So there is also a nice space of nice ball of certain dimension, and there is a kind of a lot of research is going on in this direction. But that's not the aim for me. That's not the aim of my lecture in this short time. Okay. So what I want to do, I want to consider another group, which is the group of isometries of the complex hyperbolic space. Okay. So but before that, before that I just want to give you one information, that whatever I said, like description of this space in general, or a kind of proof of all these correspondence. Okay. So you can much of it you can look at. So there is a book by M.S. Raghunathan called Discrete Subgroups of Lie Groups. So he has a chapter, Discrete Subgroups of Lie Groups. So a general discussion about these spaces can be found there. Chapter 6. Yes. So the general discussion can be found. So this is related to some old work by Andre Weil, and he essentially kind of discussed that result. But his approach is more general. So you get a general feeling about these objects. But if you want to look at the real geometric structure, then it depends on the target group that you are taking. Okay. Any questions so far? Yeah.
In the afternoon talk, we saw the Teichmüller space as a
This group gamma, you take a discrete subgroup of PSL2R. Okay. And the surface he was talking, those are compact surface without punctures, right? Or with punctures? Without punctures. So, if you take surface without punctures, then you don't need this condition. The only condition is that rho of alpha is loxodromic element or hyperbolic element. Okay. So now that means you take this discrete subgroup, which is called a totally loxodromic subgroup. That means all elements are hyperbolic. Then in PSL2R, what happened? The hyperbolic elements are conjugate to R inverse. You know that, or you don't know that has not been taught. Okay. Okay. So I will give you a brief thing about that. Okay. So let's take a digression, because this question has arisen. So we are talking about, this is also relevant to what we are doing. We are talking about PSL2R, right? So these are the isometric group of the hyperbolic space, which is like a unit disk. Yeah, unit disk. Now you can check. And the group action is Z goes to AZ plus B by CZ plus D. Yeah, AD minus BC equal to 1. F. Now if you consider fixed points of F, how many fixed points it can have? It can have at most 2 fixed points. Yeah. So F can have at most 2 fixed points. So it is called elliptic if f has a fixed point on D2. It is called, and if this action also extends to the boundary circle, so the fixed point can lie either inside the disk or in the boundary. Now suppose it has no fixed point inside the disk, okay, then how many fixed points it can have on the boundary? It can have at most 2 fixed points. Okay, the reason is the following: suppose it has another fixed point, yeah, then you join these 2 fixed points by a geodesic, and then you join maybe so then what happened? You join these 2 fixed points by a geodesic, and so there is another geodesic that join these 2. I mean, so you get a triangle, right? And the center of mass of the triangle, that has to be equidistant to everything. So it has to fix another point in the well, I mean, I am drawing a wrong picture here, but anyway, so the picture has been messed up. So, but anyway, no problem. So D2 bar. So this is so if it has 1 fixed point inside the it has 3 fixed points on the boundary, then it fixes everything. You can also see it in a concrete way. So like, if it has 3 fixed point, then using cross ratio you can prove that it fixes everything. So if it is not elliptic, it can have at most 2 fixed point on the boundary. It is called hyperbolic if f has 2 fixed points on S1. It is called parabolic if f has unique fixed point on S1. Okay, and this is a trichotomy. There cannot be any other type of isometry or any other type of Mobius transformation of the unit disk. So now, so do you know this result that PSL2R acts transitively on isometry group and doubly transitively on the boundary? Don't know. Okay. So what happened that this isometry group, if you take any 2 points inside the disk, you can always find one isometry that maps P to Q. So this is called transitive action. So PSL2R acts transitively on the unit disk. And on the other hand, on the boundary, if you take 2 points, P1 and Q1 and P2 and Q2, you always get one element from PSL2R that maps P1 to P2 and Q1 to Q2. So that's a kind of remarkable property. Using this property, up to conjugacy, you can always assume that if something if something fixes 2 points on the boundary, then those points are 0 and infinity in that upper up space model. Okay. So up to conjugacy, you can have elliptic transformation as this form. So this requires some proof which I am skipping. Parabolic transformation are just upper triangular matrices, and hyperbolic transformation are diagonal element of this form. Okay, up to conjugacy. Fine. And this is if and only if trace of a element is always less than 2. This is if and only if the trace of the underlying matrix is always 2, and this is if and only if trace of A is greater than 2. So this way you can even detect the types of the isometries algebraically using conjugacy invariance like trace. Fine. So now if you have a hyperbolic isometry, okay, so it fixes 0 and infinity. So you have so let's just talk about upper up space model. So this is, for example, a geodesic joining 0 and infinity, right? So this geodesic projects to a closed geodesic in the fundamental group, and you can talk about its length. Okay, so that's how the length appears in the correspondence that you are mentioning. But in higher dimension, the situation is not so simple, because there may be more kind of geometric invariance that can associate with, because you are no more in a 2 by, so essentially the length of a geodesic, you know, is the trace in dimension 2. So this length can be expressed in terms of trace. Okay, but in higher dimension, if you take conjugacy invariance of a matrix, there can be more conjugacy invariance. But yes, some analogous study can be made, that how you can relate one this deformation space or the higher dimensional Teichmüller space with length type kind of tuple. Yeah, that can be made. Have I answered your question? Okay. Okay. So anything else you want to ask? Okay, fine. So now I think I will come. So I am almost kind of near to the end of my talk. So how much time I have? 1 hour? 5:30, right?
Yeah,
5:30. Okay, so 10 minutes. So I will briefly tell you what is this object called complex hyperbolic quasi-Fuchsian spaces. Any questions so far? Okay. So we talked about Fuchsian representation. When you have G equal to PSL2R and you take the discrete faithful type preserving representation into PSL2R. Now you replace G by SU2, 1. So what I will do, you know, I will SU2, 1. Okay. So at the moment I will not tell you what is this group, except what is this group U2, 1. So this is group of 3 by 3 matrices such that they satisfy this condition. Okay, where J is -1 0 0 0 1 0 0 0 1. Just take it. And what is the significance of this matrix? I will come back, but after telling you what are the main objects of my title, because otherwise I will not have time to say that. So the Fuchsian representations were discrete faithful type preserving representation into PSL2R. Now a complex hyperbolic quasi-Fuchsian, a complex hyperbolic quasi-Fuchsian representation is a representation rho from pi 1 sigma to SU2, 1 such that rho is injective like before, image of rho is discrete, rho is type preserving, okay, and then rho is geometrically finite. So for discrete subgroups of PSL2R, type preserving automatically implies geometric finiteness, but for SU2, 1 it does not. So we have to add this condition. So all discrete faithful type preserving geometric representations are called complex hyperbolic quasi-Fuchsian representation, and the space of all such representation, or you know, their image is called a complex hyperbolic quasi-Fuchsian group, and the space of all such representation is called complex hyperbolic quasi-Fuchsian space. Okay. So QC, okay, so So QC sigma is a subset of Hom pi 1 sigma SU2, 1 modulo SU2, 1 consists of these representations. So now question, for Fuchsian representation, we know, right, how these representations are sitting inside this space. We know it's a connected component. Now the question is how to understand this space. Even though there are many works in this direction, but in general this space is extremely hard and not much is known about this space. So any result that you can ask for Teichmüller space can be asked for this space as well, and most of the answers are not known. For example, how this space is sitting inside this representation space. Or one big question is, I mean, this set is a subset of this space, right? How the boundary of this space looks like. So there is no understanding of, even it is not known whether this space is connected or disconnected inside that space. Okay, so this is a kind of wide open kind of generalization of the classical Teichmüller space from this viewpoint, and nothing is known. Okay, fine. So there are many problems associated to this, and there are some people who have worked on this problem also. So still a lot of I mean, one needs to develop some machinery to understand these spaces, which is still not known. Okay, though a lot of work has gone into this picture, and many people have used computer experiments to understand many aspects of this space, but still most of the questions are not known. So it's a kind of wide open object, but very difficult object, I would say. Fine, but nevertheless, I think since we are discussing this space, I have not told you what is SU2, 1 and how it is related to hyperbolic geometry. So let me just quickly recall what is a complex hyperbolic space. So you have seen about hyperbolic plane, right? So this complex hyperbolic plane is the complex analog of real hyperbolic plane. And so let's do one thing. Let's take a field R or C. Okay, take a vector space, three-dimensional vector space over F, and give this vector space this bilinear form: Z1 W1 bar plus Z2 W2 bar minus Z3 W3 bar, right? So this is a non-degenerate bilinear form. In case of real, it is a bilinear form. In case of complex, it's a Hermitian form. Now one can also give a equivalent Hermitian form, which I denote by ZW2, that is Z1 W3 bar plus Z2 W2 bar plus Z3 W1 bar. So you know when two Hermitian forms are equivalent, right? That means this Hermitian form, it is Z J W bar star, right? Where J is 1, 1, minus 1, and this is Z J2 W bar star, where J2 is 0, 0, 1, 0, 1, 0, 1, 0, 0. So you know, right, every Hermitian form can be represented by a matrix, right? So equivalence means these two matrices are sort of equivalent. That means bar, of course, bar, yeah. No, if you don't take bar, then oh, I see, I understand what you are saying. Okay, it's a kind of notation, yeah. A star, okay, star, yeah. Okay, fine. Transpose, yeah. Okay. So if you take this matrix C, which is 1 by 2, 0, 1 by 2, 0, 1, 0, 1 by 2, 0, minus 1 by 2, then C J1 C inverse is J2. So that means these two Hermitian forms are equivalent to each other. Okay. So there are many other Hermitian forms that you can take, but let me quickly define the complex hyperbolic space. So now this, so let's talk about the first Hermitian form or the second, whatever. This decompose this space into three disjoint subsets. Take, you collect the vector of the same sign, and also you have a set which is a collection of vectors of length 0. So this whole vector space V, this is a disjoint union of V naught, V plus and V minus. So now in topology or linear algebra, you know that you can consider the set of all lines and define a projective space. Yeah. So P is a map from V minus 0 to the projective space. Yeah. So now linear algebraically, the hyperbolic plane over F is the image of V minus under this map, and the boundary is P of V naught. Very abstract definition. So I am just considering the projective image of the vectors of negative length as the two-dimensional hyperbolic plane, where F can be real, F can be complex, does not matter. Now, how you are recovering the usual way of the usual hyperbolic space? Let me just tell you that. So what happened? What are the vectors of V? Z1, Z2, Z3, right? And when you are taking them in the projective space, it is well defined up to a scaling. Now, because of this condition that ZZ less than 0, what do you have? You have mod Z1 square plus mod Z2 square minus mod Z3 square less than 0. So Z3 cannot be 0. It is always non-zero. So you can scale that and you can take this representative of the same vector. Okay. So now if you call it W1, W2, 1, then plugging into this relation, this gives you W1 square plus W square 1 minus 1 less than 0. So that means this space PV minus that has a 1-to-1 correspondence with the all two tuples of vector such that W1 square plus W2 square is less than 1. What is this when W1 and W2 are real number? This is the unit disk or unit ball, right? So that gives you the ball model of the hyperbolic plane. And when F is a complex number, this gives you a 4-dimensional ball, which is a model for the complex hyperbolic plane. Okay. And using the other Hermitian form also, you can get a kind of nice model. I would end here that whenever you talk about hyperbolic plane, there is a metric associated to this. Now, what is that metric? So that metric in this setup is called a Bergman metric, and it can be defined in the following way. So you have two kind of so you have 2 points Z and W in the complex hyperbolic or real hyperbolic plane. You leave them to F3, okay, and then you have the inner product there. So in terms of inner product, you can define this in this same way, in this way, okay. So this will give you the normal hyperbolic metric that you are talking about. Fine. So this gives you a model for the complex hyperbolic plane or the real hyperbolic plane. And you started with this bilinear form, this one. Now in linear algebra, take set of all matrices which preserve this Hermitian form. So that matrix is precisely U2, 1 because this satisfies this J, Z, J, W star. So any matrix that satisfies A, J, A star equal to J, that means which preserve this Hermitian form, consider the set of all such matrices as U2, 1 in the complex case. In the real case, that is denoted by O2, 1. And that gives you the isometric group of the corresponding model of the real or the complex hyperbolic space. So in the complex case, we normalize them and take the determinant 1 matrices. In the real case, also you can take SO2, 1, but you have to be careful because in the real case, SO2, 1 is a disconnected group. So you take the connected component of that group which preserves the hyperboloid ball. Okay. So this way you can connect linear algebra and hyperbolic geometry. So there are some more, the kind of classification that I have given, elliptic, parabolic, hyperbolic, that also holds true for SU2, 1 as well. And the type preserving representation accordingly can be defined similarly. Okay. So I think with this I would like to stop here. So I have tried to give you a gentle introduction to complex hyperbolic space and the deformation theory of discrete subgroups into the isometric group of the hyperbolic planes. So one of the theory you are already seeing since the last 1 week, probably without realizing that it can be interpreted in the same way. Now one kind of good problem would be to generalize some of those results in the complex hyperbolic setup. So thank you.
Any questions, comments?
I think, yeah, thank you.
So we meet tomorrow at 10. Okay, please be on time. 10 to 12:30, but we'll have a tea break at 11 o'clock. Okay, some don't waste my tea or tea other. And then 12:30 to 1 is class discussion, closing session. We finish around 1 o'clock. Should be okay. Unless you keep asking questions to sir, which you are most welcome. Tomorrow is the last day and take all advantage of this weekend. So, yeah. Feedback form should be filled and certificates to eligible certificates will be distributed tomorrow. Those who are not there will get statements.
Niranjan, এই ফোল্ডারটা দাও।